We are learning L'Hopital's role recently, and when I see indeterminate forms, I usually use Taylor series and L'Hopital's role to solve this kind of problem. So I want to introduce Taylor series here. Okay, to prove that, we need to recall mean value theorems. That epsilon c is equal to fx minus fc over x minus c, and take this to left hand side and move everything to right hand side. We will get a first order approximation of fx p1x, and what we need to do now is to find a better approximation of f of x. So we got a remainder to a term that can help us to make the approximation better. And when we approximate infinity times, we will get the original f of x here. Okay. Well, and we need to do to get p2 of x is to apply middle value theorem again here, and we will get p2 prime of x as this form. Since we are expanding the f of x on c as equal to c, so there is already a term fc in the approximation. So all the remainder terms will be just all remainder term on c will be just 0. There's no constant term in these remainders. So we just plug in and we just do the anti-derivatives and get this, and we don't know what the k is. We need to discuss for when we plug in the p2 into the form we want to get. So just plug in here, and p1 is here, and remainder term. Okay, just plug in c. So this term will be 0, and this term also. So k have to be equal to minus, because this is c, so k is equal to minus c epsilon c, and here is a term that is not eliminated, so we need to add this term to k. And finally, we will get r1 of x is equal to f twice the derivative of c of x when x is equal to c over 2 factorial times x minus c squared. And what we're going to do the further approximation is to assume that p3 is equal to p2 plus p1 plus r second order of x. Alright, yeah. And we will repeat the procedure above. Just apply the mean value theorem as f prime 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 c, and just do a recursion, and you will get the R2 is equal to third derivative of x. Now plug in c over 3 factorial. When we use the mathematic induction, we will get fx is actually fc. Actually in this form, alright. And let's prove. Okay, I'm not going to do induction. Sorry. And here's a common Taylor series we may see in our textbooks. A function we may see. The first one is sine x, and we need to find all the derivatives of the function, right? So 0 derivative is sine x, and first derivative is cosine x, and it will be negative sine x, negative cosine x, and it will be sine x, right? So it will simply just, we want to approximate it from s is equal to 0. So s equal to 0. So the f0 is 0, sine 0 is 0, right? And cosine of 0 is 1. And this is 0, and this is negative 1. So we'll get this. And back to here, 1. And here. Okay. That's our Taylor series for sine of x. And the same for cosine of x. But the sine and cosine of 0 is 1. And here, this is first power, second power. So here we will just do this. So we will get x squared over 2 factorial plus x4 s to the 4 power and over 4 factorial, and so on. Okay. And e to the x, this is kind of special because the derivative of it is simply itself. So we still use x is equal to 0 to approach the e to the x. So it will simply just 1, every f prime of c, f prime of c is just 1. So the 1 plus x over 1 factorial, and so on. Mistake. Okay, this one is, yes, it can be a Taylor series, but what we learned in our high school, we already know what is this, right? It's a power series, just like we learned that 1 plus r, the ratio is r, and when r is between 0 and 1, we will get this. We will get the infinite terms of the power series. The sum of power series will be just 1 over 1 minus x. So it will be 1 plus s squared plus x third power plus s to the fourth power, and so on, right? It can also to be done by power series, to be done by Taylor series, but it's not easy to do the differentiate for many times, and plugging is annoying somehow. And since we have minus x here, and why if we just plug in the negative x on here, we will get the next one. 1 over 1 plus x, just plug in 1 negative s here, here. Alright, so we will get 1 minus s plus s squared minus x to the third power plus x to the fourth power, and so on. Okay. This is the function we have to discuss. And we already know, we can already solve this from the previous result, because this is just equal to integral of 1 minus x and negative sign here. So it's equal to negative sign of 1 minus x is equal to 1 plus x squared plus x to the third power plus x to the fourth power, and so on. And I forgot to do this. For x, is the absolute value is smaller than 1. And not equal, and this is the same. Okay, so we will get, since the ln1 is 0, so the constant term will also be 0, so we can just integrate this, and c plus c is 0, minus s half of x plus 1/3 of s to the 3 power, and so on. Let me adjust the size, right? Just negative s minus half of s squared minus 1/3 of x cubed, and so on. Okay, s is, because we use this, so s is also smaller than 1, absolute value. Alright, 1 plus x, we have the result in here, so we just plug in the negative x, so we will get s minus 1 half of x squared plus 1/3 of s cube, and so on. And the boundary is the same. Okay. 10 arctan of x is equal to the same way to do that. So we'll get 1 plus x squared. You may wonder, there's no 1 plus x squared in this slide, but as you can see here, we can just plug in x squared to here. So we can get 1, let me see. 1 minus x squared plus x to the 4 power minus x to the 6 power, and so on, right? And it will be, oh, forget the dx. It will be, since when x is 0, arctan of x is also 0, so the constant is also 0. So we will get x minus 1/0 s to the 3 power, and so on. Oh no, mistake. And the boundary is the same. And we know that is just 1 minus s squared dx. So all we need to do is apply this. So we can get 1 plus s squared plus x to the 4 power plus x to the 6 power, and so on dx is equal to s minus 1/3 x to the 3rd power, and so on. Oh, O plus. Sorry, mistake. Boundary. Okay. And I usually do use Taylor series to solve L'Hopital's rule. To solve, mistake. To solve indeterminate form of limit with L'Hopital's rule. And this is an example. We can expand it. The numerator and denominator both expanded. You can just do s minus s to the 3rd power over 3 factorial, and we can just leave it here. And x times, and when the x is not the original x, instead it is the s to the s squared. We just need to plug in the s squared to the x here. So we will get s squared minus s to the 6 power over 3 factorial plus O is 8 power. No, 10 power. So we will get limit s to 0 and negative 1 over third factorial s to the third power plus the remainder over s to the third power minus remainder is x to the 7th power. Okay, and we will see, because the remainders are smaller than the s to the third power, because the s is approaching to 0. And what we need to do is the same as when we are doing f prime of we are doing the derivative of s to the 2 power, just like we have this, and the definition is minus x minus, oh, mistake, oh, sorry, s plus delta x squared minus s squared and over delta x limit delta s is approaching to 0. And in here we will get a delta x squared term, but since the delta x is already approaching 0, so delta x squared is so small that we can ignore that. So we will get just the coefficients of s to the third power. So the answer will just be positive. Sorry, because this is a negative, and here also. So just a positive 1 over 3 factorial is equal to 1 over 6. And the same is here. Arctan or x, we'll get x minus 1/3 of s to the third power. So x minus 1/3 of s to the third power, and I think this is enough to do this. And minus x s times x minus 1/3 of s cubed, and that's enough. And we will see x will cancel out, and the terms that this is the third power and this is a cube, x cubed. So since we discussed here, s cubed is much greater than s to the third power, so we will just get 0 as the answer. Well, this is the problems. This is a problem I'm seeing on the textbook and our homework. And we just need to take the s squared to wait, let me check. Yeah, just take the s squared to a denominator. Okay, and it seems not so good to do the Taylor series, but we need to do the u substitution here, as u is equal to 1 over x. So we will have limit u goes to 0 plus and u minus natural log of, and we need to calculate this. 1 plus 1 over u divided by 1 over u and multiply both sides of u. So we will get natural log of 1 plus u, and we'll get u squared here. And this is the form that we can do Taylor series. So we can transform it into u minus, and we can check the Taylor series. Oh, sorry. 1 plus x, so we will get u minus 1 over 2 s squared, u squared, and I think this is enough for it. So we will get OU3, remainder is third power, u squared, and this and that will cancel out, and we will get just negative 1 over 2, so we will get 1 over 2 as the answer. Oh, and this may not be a good form to use L'Hopital's rules, because when you apply a L'Hopital's rule, this term and this term will be chaos, and it will be uglier than the form that you haven't used the derivatives on both sides. But this form is easier to use Taylor series to deal with it. So sin x is equal to x plus s minus s to the third power and 3 factorial, and we'll get plus this, and I think this is enough. And e to the s squared, so we have to plug in s squared to e to the x plus s squared 1 factorial plus s to the third power 2 factorial. No, s to the fourth power 2 factorial, and I think this is enough. And then I need to change the size, maybe smaller. Okay. Then put arctan here. Minus x minus s minus x to the third power over 3, and I think this is enough. Okay, and the denominator is just x to the third power, and the other term is too big. The power is too big, so we will leave it here. No, ninth power. Okay, let's see the coefficients. Wait. Okay. We'll see that x, the first power will be cancelled out by this. And the second power, less is indeed second power. No, there's no second power here, because this is second power and this is the first power, and the one here only can multiply to odd powers, so there's no second power here. And the third power, we can have this times this, and this times this, and we will have another third power terms here. So the coefficient is 1 here, and minus 1/3 factorial here. Oh, mistake. 1 is from here. 1/3 factorial is from here, and just plus 1/3. Oh, and multiply. Oh, ugly 3. Multiply s to the third power, and everything is just remainder. So okay, x to the 5 power is a remainder, and we will get the bottom is keeping as s to the third power remainder, and the answer is obvious, just 1 minus 1/6 plus 2/6 is equal to 7/6. Okay, the introduce of Taylor series is end here. Thank you.